check it and change them, and I didn't. So hopefully I don't lose battery. All right. So you have an assignment due tonight, so don't forget about that. We are starting and we'll get through most, if not all, of 4.3 and 4.4. In WebAssign, this is a combined assignment. So there'll be only one assignment that covers both these sections. It's not two separate assignments, okay? So just FYI on that. Also, after this is the unit quiz. So we're looking at like Monday or Wednesday of next week for the unit quiz. So just have that on your radar. Okay, so. All right, this first part, so in 4.1, we talked about exponential equations, right? So what is the exponential equation model? What do we use? It's not y equals mx plus b, that's linear. What was the exponential one?
And then it was raised to 15.
All right, so let's remind ourselves, what is n? Function. What is p? Initial value. A. And that factor can represent what or what?
Growth, okay.
Correct. And then T variable. All right, so these are all the pieces that we've been working with in this new unit. Okay, so we're going to continue that. If you look at example 1, it says decide whether the data is exponential. Okay, so if you recall when we were talking about linear, it was when the average rate of change was constant. When we're talking about exponential, then we're looking to see if it has a constant factor, which represents a constant percentage growth or constant percentage decay. Okay, so let's look at this first table. Still holds true that this is always our variable and this is always our function. Now, you can actually look at this table and tell me, do we have growth or decay? Growth. You can look at the function and see that it is getting bigger. So we know we have growth. Okay, so that means our growth factor, what type of a number does that have to be in order to be a growth factor? Greater than 1. All right, so you guys are remembering stuff. That's good. All right, so when this question says decide whether, it's actually asking you to show or to prove that it is an exponential or data that represents exponential. So when we were talking about linear, we would calculate the first two and find the average rate of change. We would take the last two and calculate the average rate of change. So we're still going to choose the first two and the last two, but we're not finding the average rate of change. What we're going to do is divide to find that factor. And the letter we use for the factor is A. So I would take 6 divided by 3 and get 2. And then I would take 48 divided by 24 and I would get 2 as well. So what we have shown is that we have a growth factor. And that number definitely is larger than 1. So I would say that growth factor is 2. And it is constant, right? So, and you can look at this, like my 930 class had a student say, oh, they're multiplying by 2, which in essence is what is occurring, right? It's not always as easy to see, because if you look in the second example, again, we still have our table with our variable and our function. And in this one, I can tell that I have growth as well. So I know I'm gonna have a growth factor because that is increasing. But I can't look at this one like the one above and go, oh, they're multiplying by and tell you that number. So what we're gonna do to determine, decide, or show is we're gonna do this division. You're gonna take the first two and do 1.66 divided by 1.26. And then you're gonna take the last two, 2.89 divided by 2.19. So if you'll calculate that and give it to me, 2 decimal places will be sufficient. Did it occur on both?
Yeah.
Yes, okay. So what we have found is that our growth factor is 1.32, which that number is definitely larger than 1, so we know we're good. And it's constant, meaning what they did is they multiplied by, they took this times 1.32 times 1.32 times 1.32. It was a constant percentage, okay? All right, now, just like when we dealt with linear, if it had a constant average rate of change, we knew it was exactly linear, but then we got into linear regression, where the average rate of change was not constant, but if we graphed it, it took on the characteristics of a linear relationship. The same is going to be true with exponentials. So what we're going to learn to do is this right here, which is dealing with the exponential regression model. So when you see that word regression, you know it's not an exact relationship, but it does have characteristics of being exponential, okay? All right, so we're gonna follow these steps with this table here, just to learn the steps. So, see, my batteries are low, hopefully it won't go out on me. Okay, so even before we start this, go to y equal and make sure that your plot is on. Because we're gonna be plotting points, so be sure plot 1 is highlighted. If not, just cursor up to it, hit enter, and then make sure it's highlighted, okay? Then what we're gonna do, which we did, we've done this before, we're gonna enter our list 1 and list 2. So we go to stat, edit, which is 1. I told you guys to clear yours out and mine weren't clear. Okay, so 0, 1, 2, 3. Right arrow over 1.26, 1.66, 2.19, 2.89. Okay. So now we want to plot the data. What do we need to remember to push in our calculator to plot the data?
Zoom out.
Correct. So it would look like this. So what this is doing is increasing at what kind of a rate? Increasing rate, right? It's increasing at an increasing rate. Okay, now what we're doing is we're learning how to find the equation. And so these are the pieces to the equation that we need. So we need the initial value and we need the factor. Okay, so the two things that we're going to look for are the initial value. And then we need, and we already talked about this was a growth, so we're gonna look for the growth factor. All right, so we've got everything in, we plot the data. So now go to stat, right arrow over to calculate, and then press 0. So prior, we did 4, right? The linear regression. If I go down to 0, it's exponential regression. So you can cursor down to it, or you can just push 0. Then you're gonna just continually hit enter. And you're gonna get this information. Okay? Okay, now we need to have a discussion right here. Because for us, the growth factor is A, correct? Okay, well, we've got to be careful in our calculator. So here is our exponential model equation. If you'll look at the calculator right here, for the function n, it uses the letter y. For the initial value p, what is the calculator using? A. For our growth factor of A, what does the calculator use? B raised to the x. So you have to be careful on this because the initial value that we call P in the calculator is actually A. So you're gonna need to be careful of that. Just remember the initial value is always the first one that they give you. And I'm gonna go out 3 decimal places, 1.259. Yes, no? Something different? Go back to your list and make sure you got the numbers in there right. I'm gonna guess either your X or your Y values, or you have a number entered in your list incorrectly. If it's not that, I'll take a look at it. Okay, hang on, let me finish this and then I'll come look at it. Okay, so then the growth factor that we call A, the calculator calls B, which rounded to 1.319. Everybody besides 1 is okay on this? Okay, so now I can put these values into our exponential model. So my function n would equal the initial value 1.259 times the growth factor 1.319 raised to our exponent t. And this makes sense in relationship to my table, because look at your table. What is the initial value on the table? The variable is 0, so what is your initial value? 1.26. What is this rounded to 2 decimal places? 1.26. They have the same initial value. What did we calculate the growth factor to be? 1.32. What is this growth factor rounded to 2 decimal places? 1.32. Okay. All right. So while I look at his calculator, what I want you to do is I want you to go into your calculator and enter this data. We're doing this one. We were doing this one. Now we're getting ready for this one. So just jump down to this one and then let's make sure it's okay. You were jumping ahead of me. You're like, no, those numbers are right. So, all right, let me go back to my list. Okay. All right. So while you were entering that, now let's backtrack and just read the problem and see what's going on. On a particular space vehicle, the nuclear energy source that supplies power to the vehicle loses energy each day. The data is given below. Okay, what type of exponential relationship do we have here? Look at the table and tell me what's occurring. It's decreasing, which means we have decay, right? So we know it's decreasing, which exponentially that represents decay. So we know if it's going to ask us to create an equation, we know that that factor will be a number smaller than 1. So those are all the things you need to make sure of, so you don't give me something funky like a factor of 29.32 or something like that, okay? All right, show that the data are exponential by plotting the points. Okay. Want to remind you all on the test, I had to circle and count points off, and my comment was, you did not label, always label. So please don't forget that. All right, we know the vertical is our function. So that's W, which is watts of hour. And then we know our horizontal axis is the variable, which is time, or T, time in days. All right, so you already went into stat, edit, and you entered list 1 and list 2. All right, so now if we want to plot those, what do I hit on my calculator? Zoom 9. All right. So zoom 9. Now it almost looks like a straight line, doesn't it? It looks linear, but in all actuality, this is slightly curving here. So just FYI on that. So if I did this kind of like that, okay? Now, part B says write the exponential equation that represents W as the function of T. All right, to write the equation, we need two things. We need the initial value and we need the factor. All right, so where do we find that? You're going to go to stat, arrow over to calc. Now, instead of 4, that was linear regression, we now push what? 0. Okay, so stat, right arrow over to calc, and then you can just push 0, enter, 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 enter. Now do you get the same numbers as I do? Please be a yes. No? Did you get what I got?
Yeah.
Oh, perfect. Okay, so we know the initial value to be P. It'll always be the first one, which is A in your calculator. I'm going to go 3 decimal places, 75.002. The factor, now we already talked about, the table showed us decreasing in decay, so it definitely makes sense that our factor A that the calculator calls B is the number 0.996 that is smaller than 1. So all that stuff lines up. Okay, so the exponential equation model is this. I need to be sure that I use the appropriate function and variable letters, okay? So I'm not going to use N. My function now is W. We found P to be 75.002. We found the decay factor to be 0.996. And then if you gave me capital T or lowercase, I wouldn't care because here it's a capital, here it's a lower, so either one is fine. So that would be my equation, okay? All right. The estimated number of multimedia personal computers in homes is given in the table. Okay, so PCs, personal computers. Computers. All right, so my function is the number of computers in millions. So two doesn't mean two computers, it means 2 million. Well, obviously, this is showing what? Growth, right? We definitely have, it's increasing, so we have growth, which makes sense, right? This is year 1992, 1993, and so forth. Okay, so it says plot the data. Okay, so now we gotta go back to stat, edit. We're gonna clear out the numbers that we have. And then we're gonna enter the new ones. 0, 1, 2, 3, 4, 5. 2, 4.1. 8.1. 5. 1.4. All right, and after we enter it, what? Zoom 9. So in plotting, vertical function in, which is, I'm gonna write number of ECs. And then we need to know we're talking about millions. And then variable is T years since 1992. Kind of something like that. It's not exact, so, but obviously I'm gonna have flexibility on that, okay? Now, does it appear reasonable to fit an exponential model? Okay, how do we know when it is an exponential model? It's because it's either increasing at an increasing rate, which would give you growth, decreasing at a decreasing rate, which would give you decay. Okay, so what's going on here? So it is increasing at an increasing rate, and what? This is the number of ECs is increasing at an increasing rate, which represents exponential growth. So that's how we know that it is an exponential model. Because when we first learned increasing at an increasing rate and all that, they have these same type of graphs. We just hadn't had the discussion about exponential equations yet. All right. Find the exponential regression equation for this data and graph it on the plot. We got to do two things. Okay, so to find the equation, we need to get the initial value, P, which is A in your calculator, and then we need the factor, which is B in the calculator. Okay. All right. So stat calc 0. This is, we need, whoops, we need to write it stat calc 0, and then hit all the enters. All right, so it appears my initial value, which again is always the first number, I'm going to go 3 decimal places, so 2.355. So look at your table. It's not gonna be exact because we don't have a perfect exponential equation here. But again, it's close. If this would have calculated to be 200, we'd be going, oh, wait a minute. And then our factor, 1.748. You already told me that it represents growth. That number's larger than 1, so everything's lining up. Okay, so the equation, we start out with the function. So I look at my table. N is what we use for the function. Initial value, 2.355 times growth factor, 1.748, raised to the variable, which I look at the table, and that is T. Here is this. Now it wants me to graph it. Okay, so in order to graph it and put it up here on the graph, what do I do? Yep. Y1 equals, and put in that equation. And be sure you raise it to the X, because if you just multiply times X, it's not going to be correct. Okay, now what do I hit? Graph. And as you can see, it doesn't go through every point. Ish. Okay. Okay. What is the approximate yearly percentage growth rate? So it's asking you for a rate. So think back to what we did in 4.1. Where does the rate come from? The factor. Okay, so in this particular problem, we have a growth factor. And if you recall from our earlier discussions, that was found by 1 plus R. So what we're looking for is that rate. Well, we know in this problem, the growth factor is 1.748. So basically what we want to do is eliminate the 1, and what are you left with? This number that is that becomes your rate. So we know the rate is 0.748, but we want to represent our rate as a percent. So what you need to know is that to convert this to a percent, you move the decimal 2 places to the right. So our rate is 74.8%. How many multimedia personal computers would you expect in homes in the year 2001? What's given? Okay, so given variable value, which is T. So is T equal to 2001? Go back to the table. What do we have to subtract from that?
1919.
Yeah, since 1992. So it's actually T is 9 years. So now we're going to take our exponential equation and we're going to find N at 9, which will be 2.355 times 1.748 raised to the 9th power. So this is just a matter of plugging this in. And hit enter. And I'm going to go 3 decimal places. $358.809 what? Million PCs. That's a lot. It jumped up there quick. In how many years will there be 100 million multimedia personal computers in homes? What was given? Mhm. And my function is in, and this is saying 100 million. Okay, so what we're gonna do is we're gonna use this equation, but in place of this in, we're gonna put 100. So we would have 100 equals 2.355 times 1.748 raised to the t. This is already in my calculator as y1. What do we now do with this? Okay, now this is where it might get interesting, depending upon what the window is. So I'm gonna go in here and put in 100. And I'm gonna go to my window and it sets some numbers up. I have no idea if that's gonna be good or not. There's my exponential. I'm not seeing the other line, right? So this, think about this. This, you told me, was the function value. So when you go to the function value, this in your calculator is your X and your Y. So I look at my Y maximum. Well, no wonder I can't see it because this is set at 36. I'm gonna put in 125. And now I'm gonna take a look at it. Did it take it? Doesn't look like it took it. I don't think it took it. No, it reverted back. Huh. It did last class period. I wonder why it's not now. Did it for y'all? See how mine's reverting back? What did it do on y'all's? Let me try something else. You guys aren't talking to me. What'd y'all's do? Did it change on y'all's? Whoops, I hit the wrong button. There it is. I think I did Zoom 9, which would be just my plot points. I needed to do Zoom 0. Is anybody else getting the intersection? What is it doing? Brett told me what his is doing. What is yours doing?
Mine just has a line over it. Like you can't see the full intersection.
Okay, so let's see if it'll, even Brett, let's see if it'll give us, even if it's not in your window, let's see if it will still give you the intersection. Okay, so go to stat. Calc. No, disregard. Disregard. Go to second calc. Second calc. Intersection. Did it come up first curve?
This is no sign.
6.712.
So did you get numbers? You don't have your, oh, yeah, you do. You did a wide min, I don't want, you did both of these as zero. That's why. That is zero. You can't have the min and the max the same. I would just did the Y max the same. I'll have to look at it after. I can't keep looking at it. We'll have to look at it. What I would do right now, shut it off, the whole thing, and then turn it back on. Okay? Anybody else get anything weird? What are you getting?
Mine is error, error, mountains.
Okay, so let's move on, and I'll work with you guys after and see if we can figure it out. But again, I'm gonna tell you what I told Brett. Go ahead and shut your calculator off and back on and see if it resets. If not, we'll, look at it after class. Okay, so be sure you get the notes taken down though. So once you get the intersection, you get x equals 6.712 and you get y equals 100, okay? X in our calculator is the variable, correct? And our variable in this particular problem is t equals 6.712 years since 1992. And this asked how many years, and we have answered that. Okay? All right. So just know, those of you that are having calculator problems after class, let's go back to that one. But I need to get through, let's see if you turned, so this is variable, this is function. So go ahead and clear out your equations as well as your lists. Brett, was your plot on?
Yeah.
Okay. Okay, so go ahead and start entering this information, which is talking about lead emissions in the environment from the years 1970 to 1980. So 0 means 1970, 5 would be 1975, and so forth. And then lead emissions are millions of metric tons. What is, looking at the table, what's going on? It's decreasing, so we know we have what? Decay, okay? So explain why this data is nearly exponential. All right, so let's go ahead and graph it and take a look at what is going on. So I'm going to do Zoom 9. You guys get that? Okay, good. So far, so good. Okay, so as you can see, we have decay. So this is decreasing at a decreasing rate, okay? So we're talking about the function. So when we explain, we would say the lead emissions is decreasing at a decreasing rate, which represents exponential what? You told me just a minute ago because of the decay. So looking for the word decay or growth. So in this case, it would be decay.
Wait, so it is exponential?
Anytime it curves.
I was confused about the nearly part.
Well, because it's not an exact. So when if we were to graph our equation, it won't fall on every ordered pair. That's what the word nearly means. All right. Exponential regression equation. So we need the initial value And we need the factor. E, it's A in your calculator, A, it's B in your calculator. And this is stat. Calculate 0. Enter, 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 enter. All right, so we get 293 point, now it'd be 4, and this 9 will round up to a 10, which is gonna push this to a 5. So 450, and then 0.829. So my equation, so the function is L, initial value 293.450. My factor 0.829 raised to the variable t. All right, what is the approximate yearly percentage decay? Okay, in the last question we had like this, it said the word rate. This one does not say the word rate. So what you want to pay attention to is the word percentage. In essence, it's asking you for what is that rate. So we know in this problem, we have a decay factor. We know the decay factor is found by 1 minus R. Right? Okay. The decay one's takes a little bit more work to find. So we have A is equal to 0.829. So I need to find out 1 minus what gives me 0.829. So what you're going to do is you're just going to do 1 minus 0.829, and this will give you your rate. So somebody tell me what that is.
0.171.
Because notice here, if I put in 1 minus, if this is my true rate, 0.171, then I will get my factor, which is 0.829. Okay, so we just found the rate to be 171, but it wants it as a percent. Move the decimal 2 places to the right, 17.1%. Estimate the amount of lead emission in the year 1982. What's given? But again, it's not T equals 1982, it's since 1970. So it's 12 years. So go up to part B. And so L at 12 equals 293.450 times 0.829 raised to the 12th power. Two 293.450 times 0.829 raised to the 12. I get 30.916.
Yes.
Is that what you guys got? Okay, so what are we talking about here? Millions of metric tons of lead. Oops, can't spell emissions. Okay. All right, I want to try to get through A and B of the next one and then we'll call it a day. So. Again, clear out and enter these. Plotting points, so after we put in L1 and L2, what do we go to?
Then,
Okay, so part A says explain why this data is nearly exponential. All right, what is the function doing
increasing-
at A,
increasing
which represents exponential? Exactly. Now, the graph, what are we talking about in this problem?
The revenue.
Revenue. So the revenue is increasing at an increasing rate that represents exponential growth. And then we're gonna find the equation. So stat calculate 0. Stat calculate 0. Enter, 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 enter. All right. A, which is our initial value, did you get 0.785?
Mhm.
I'm gonna go ahead and write all this just so it's in notes. P, calculator is A. Then the factor, which we need growth. A, and calculator is B. Okay, that makes sense. 4899, that would be 0.490. So in this problem, my function is R. Initial value times growth factor raised to the variable T. Okay. All right, so I have gone